Okay, welcome back. So now that we're done with chapter one, we're moving on to chapter three, which is going to involve some basics of what a probability distribution is. And then we're going to talk about some tools we have, measures of location and measures of dispersion. And what they do is those are figures, quick numbers that give us measures of how to look at different probability distributions, different data sets, uh, so that we can get a lot of information from what might otherwise look like a fairly chaotic situation rather quickly. Okay. In other words, you could be looking at, say, stock prices of IBM, right? And you just look at the ticker all day long and you're like, wow, this price is up and down and up and down. And I wonder what's going on with this stock. And meanwhile, you just like, oh, the average of the IBM stock is, $123 today. You go, oh, okay, the average is 123. And then, how spread out is it? Oh, well, its high was 150 and its low was 80. So its range was, right, whatever that number worked out to be. And then you have an idea of what's going on with that stock price pretty quickly. Okay. So, in order to get going here, the first thing we need to do is we need to define probability distributions. Okay. The whole idea of measures of location and measures of dispersion is that we are going to be using these numbers, these formulas. Okay. We're going to get into what some people might consider to be math or, uh, we're going to introduce some Greek symbols. All we're really trying to do here is make sense of different data distributions, different probability distributions. So in order to do that, we need to first get into what is a probability distribution. Okay. So I'm going to share my whiteboard. And so we are now working with a probability distribution. Okay. And probability distribution is really nothing more. Okay, I'll give you the textbook definition in a second, but a probability distribution is really nothing more than all of the possible outcomes or values, all the possible outcomes or values that a variable can take on and the relative likelihood or frequency that that value will occur. Okay. So let's think about this. What's a probability distribution? Well, it's all the possible outcomes or values, right? Same thing, possible outcomes, all the possible values that a variable can take on, and the relative likelihood or frequency, aka probability, that that value will occur. Okay. What's an easy way to think about this? An easy way to think about a probability distribution is nothing more than all, or let's say the set. Okay. It is nothing more than the set of all things that can happen and the odds of it happening. Okay. The set of all things that can happen and the odds of it happening. Right. And that's how you could explain it to, somebody close to you, your mom, your grandma, something like that. Right. So the formal definition of a probability distribution, right? Just all the possible outcomes or values that a variable can take on and the relative likelihood or frequency that that value will occur. How would you explain that to someone, right? It's the set of all things that can happen and the odds of it happening, or, everything that could happen and whether or not it's probably going to happen, right? So let's think about this, fairly simply, right? I'm going to stop sharing for a second. Let's take probably the most well-known probability distribution there is, a coin flip, right? So when it comes to flipping a quarter, it could land heads or it could land tails. I suppose theoretically it could land on its side, but it still hasn't happened to me yet, right? So what's the odds of it landing on heads? 0.5. What's the odds of it landing on tails? 0.5. So it's what is a probability distribution? It's all the possible values a variable could take on, right? The possible values, heads, tails, and the likelihood of it occurring. 0.5 heads, 0.5 tails. Okay. Those are the two possible outcomes. Again, theoretically, it could land on its side, but, still hasn't happened to me yet. Okay. Um, or we could take a dice. In dice, when you're rolling a dice, right? When you roll the die, you could roll a one, a two, a three, a four, a five, or a six. Okay, well, what's the probability of rolling a three on a die? Right? There you go. The probability of rolling a three is 1 out of 6. Okay, so what's the probability of rolling a five? It's 1 out of 6. Okay, those are all probability distributions. Okay, it's really nothing more than the potential values that a variable could take on and the relative likelihood of that value occurring. Okay, in other words, it's everything that could happen. You could get when you're flipping a coin, you could flip heads, you could flip tails, right? So it's everything that could happen, and the odds of it happening, right? 0.5, 0.5. Okay, or we could apply that to in the last lecture we were talking about you know speeds of cars on the turnpike. Okay, well, what are all of the possible speeds of a car driving on the turnpike? Well, I suppose it could be going 2 miles an hour. I mean, theoretically, right? And theoretically, a car could be going, 140 on the turnpike. Realistically, probably not. Realistically, most cars on the turnpike are going to be going between 45 miles an hour and, let's say, 100 miles an hour. Okay. Now, are you likely to find a car on the turnpike that's driving 47 miles an hour? No, you're not very likely to find that. So the probability associated with a car driving 47 miles an hour on the turnpike is very low. You would not expect to find 47 miles an hour on the turnpike. On the other hand, would you expect to find somebody driving, 97 miles an hour on the turnpike? No, that probability will also be very low. I mean, you might find one, maybe two, but out of the entire New Jersey turnpike, you wouldn't expect to find a lot of people driving that fast, right? Speeding that much. So that probability associated with 97 miles an hour, that's probably very, very low too, right? So here we have probability distributions, right, where we're seeing like, okay, 47 miles an hour, not very likely. 97 miles an hour. Also not very likely. Where will most people be driving? Most people are going to be driving between, 56 miles an hour, 52 miles an hour, 70 miles an hour, 73, right? People are going to be clustered between probably 65 and 75, right? Somewhere in there. That's usually, in my experience, where how fast people drive, maybe between 60 and 75. Okay. So that's what you could expect on the New Jersey Turnpike, people driving between that range. Okay. So, but those are also the speeds that have the highest probabilities associated with them. Okay. People are probably going to be driving on the turnpike at, 62, 64, 68, 73 miles per hour. Those are the likely speeds. So let's go back to the definition of a probability distribution. What's a probability distribution? Well, it's all of the possible values that a variable can take on. What's the variable? How fast the car is going. That is variable. It changes. So it's all the possible values a variable can take on: 4 miles an hour, 23 miles an hour, 47 miles an hour, 55 miles an hour, 65 miles an hour, 70 miles an hour, 75 miles an hour, 88 miles an hour, 99 miles an hour, 147, right? Okay. So it's all the possible values. Those are values that the variable can take on. They can do it, but then it's also the relative likelihood or the probability of that value occurring. Okay, so yes, somebody could drive 120, but it's not very likely to happen. Somebody could drive 40 miles an hour, but it's not very likely to happen. For the most part, people are going to be driving 65 miles an hour. That is very likely to happen. Okay, so it's important to remember that a probability distribution is the combination of the value and the probability associated with that value. Okay, so it's a combination. You need to have the potential value and the probability of that value occurring. Okay, that gets us a probability distribution. Okay, now in quantitative analysis, there's all kinds of probability distributions out there. Okay, we're going to get to that a little bit later in our next lesson, in chapter 7. Okay, but there's all kinds of probability distributions out there. Okay, as we're going to see, there's really an infinite number of them. Okay, and the reason why this could be problematic, in a sense, it's really not problematic, but it could be, is because it would be really hard to discern some quick information about that probability distribution without, spending a lot of time studying it, right? So in other words, if we were trying to get a quick sense of like what's going on with the stock price of IBM, or what's going, tell me something fast about the dollar euro exchange rate, or how many cubic yards worth of tinfoil are rolling off of our presses at the Frito-Lay Dorito factory? Because the tinfoil is what makes the bags of chips, right? The actual bags. How many of those are defective cubic yards, right? Because you would want to know. That's quality assurance, quality control. How many defective Tesla batteries are being produced on the assembly line every 48 hours? Okay. In order to get a grip, a handle on these probability distributions, you would either have to spend a lot of time studying it, which is very time intensive and very costly, or you can use things that are known as measures of location and measures of dispersion, which are things you really already use. It's probably ingrained in you. You just may not call them measures of location and measures of dispersion yet, but these are concepts that you probably work with on a daily basis already. Okay. Now, before I move on to the measures of location and the measures of dispersion, which, we're going to start getting into the calculations, I want to point out here, you know, what's the purpose of this chapter, right? What are we doing in chapter 3? Well, I mentioned in chapter 1, the whole point of quantitative analysis is we're going to take samples. From those samples, we're going to calculate statistics, and we're going to use those statistics to estimate parameters. Parameters are characteristics of populations. It's the whole set, right? What we really truly care about is the population, right? We want to know, just let's say, what is the true average income of Jersey City, right? Like, what is the average income of Jersey City? We would love to know the true, actual, to the cent average income of Jersey City. But that is impossible to do because by the time you get to the last person, the first person or the 300th person or the second person or everybody's income will have changed. So in other words, it's not practical to do that. It's very time consuming again. So what we do is we take our samples, and from those samples, we calculate statistics, which then give us information about the populations. Okay. Well, in order to do so, one of the fundamental tools that we need to use are measures of location, measures of dispersion, and the measures of location and dispersion are what give us information about probability distributions. Since we are trying to estimate parameters using statistics, we need to know if our probability distributions are going to be quote unquote, accurate. If the distribution of the sample is representative of the distribution of the population. So in order to do that, we need to have some key indicators, some quick numerical summaries, if you will, some descriptive indicators that we use on a daily basis. Those quick indicators, those are our measures of location and measures of dispersion. Okay, so the whole point of chapter 3 is these are some tools that we are going to use for when we get to calculating probability distribution, calculating probabilities between different intervals in a normal probability distribution, confidence intervals, one sample hypothesis test, two sample hypothesis tests, linear regression, right? All these things we're going to be using measures of location and measures of dispersion for. So we need to get these drilled down. We need to have a good foundation in measures of location and dispersion because this is how we get information about our probability distributions. And our probability distributions are what we're going to use in order to gauge whether our statistics, our sample statistics, are reliable estimators, reliable indicators of our population parameters. And that's the whole name of the game in quantitative analysis. Quantitative analysis, we're trying to know if our statistics are representative of our parameters. So that's what we're going to get into here. Okay. So measures of location, measures of dispersion. Let's go back to our whiteboard. Okay. So in other words, we have it. So if we start here, right, probability distribution, it's all the possible outcomes or values a variable can take on and the relative likelihood or frequency that that value will occur. Let's start talking a little bit more about probability distributions, right? So when it comes to a probability distribution, let's just take, say the price of IBM stock. Well, IBM stock theoretically it could have a value of 0, right? I mean, if the company's stock price crashed today, it could go all the way down to zero. And then theoretically, let's be realistic here, it could go up to, $10,000. Okay, $10,000 before they might do some sort of a split or something like that to try to not make the price so exorbitantly high. Okay, so in theory, the price of IBM stock could go between zero and $10,000. Now, is it going to be $10,000? Probably not. Actually, let me back up real quick. So on our horizontal axis, on this x-axis, we have values. Okay, these are the values the variable can take on. Okay. And then on our horizontal axis, sorry, not on the horizontal, on the vertical axis, we have P of X, which is AKA, ooh, that's not the greatest AKA. That is the probability of probability value X, we'll see. Okay. So P of X on the vertical axis, that's the probability of value X occurring. And then on the horizontal or the X axis, we have the values that the variable could take on. Okay. What do I mean by this? Well, IBM stock. IBM stock in theory could be $0. It could also be $10,000 in theory. But are you really going to see, IBM stock be worth 10 grand? No, of course not. So the value, the probability, because remember, it starts at zero and goes up to one for probability. The highest probability anything could be is one. 0 to 1 or 100% if you want to, do percentages, right? But the value of the probability of IBM stock becoming $10,000, that probability is very low. Okay. At the same time, is IBM stock going to be worth $0? No, probably not. That value is also going to be pretty low, right? That probability is going to be low. So you have a low probability for the value of IBM stock, low probability for the value of IBM stock being $0, and you have a low probability of the value of IBM stock being $10,000. On the other hand, what's the probability of IBM stock being $183? Right? Let's just put this in here. 183. What about 75? What about 90? What about 146? Okay. What's the probability of all those values happening? Well, the probability of those values happening is probably high, right? You probably see IBM stock be worth, 146, 183, 90, 75. Okay. So you're going to see a lot of observations there. Okay. And each one of these dots that I'm making, each one of those is the price of an IBM stock on a certain day. Okay. So this one could be day 3. This one could be day 12. This one could be day 86. Okay. So to fully explain this graph that I've made here, this distribution. On the horizontal axis, we have the potential values that the variable can take on. IBM stock could be $0. It could be $10,000. It could be $75. It could be $183. Okay. What's the probability of each one of those values occurring? Well, the probability of IBM stock being $0 is very low. Right? It doesn't go very far up the vertical axis. It's very low on it. At the same time, the probability of $10,000 is very low as well. That's not going to happen either. Instead, the probability of IBM stock being $146, that probability is very high. As you can see right here, right? That probability is very high. And the same goes for the price of $90, right? That price is very high. The probability is very high. So in other words, what we have is combinations. We have a probability distribution, right? And the combination of the potential values a variable can take on and the likelihood, the odds, the probability of it occurring. That's a probability distribution, and it's key to this entire course. Okay? Probability distribution is nothing more than the combination of the values a variable can take on and the probability of it occurring. Okay? Now, where measures of location and measures of dispersion come in is as follows. Let's take this probability distribution. Okay. Okay. So in other words, let's say that each one of these are prices of IBM stock on different days. This is a high price. This is a low price. Right? And this would be the medium price. Most of the time, IBM stock is in the medium range. Okay. But then let's look at this one. Okay. Let's say this probability distribution. Okay. This is a low price. This is still our high price. And this would be a medium price. Well, look, most of the data here, if this is IBM, and this is, let's say, Under Armour. Right? Under Armour has much of its stock price clustered here. Okay. The Under Armour stock price is not as high as the IBM stock price. Under Armour is clustered between low and medium. IBM is clustered right around medium. So that means that on average, right? Now we're starting to get into quantitative analysis here. On average, IBM would seem to have a higher stock price than Under Armour. Why? On average, it has a higher stock price because most of the time, the value of its stock is found around the medium stock price. And since most of the time its value is found around the medium stock price, that would be an indication that it is likely or it is probable or the odds are good that IBM's stock price will be in the medium neighborhood. On the other hand, since on average Under Armour's stock price is usually between low and medium, that would indicate to us that we would be that would indicate to us that we are probable, or the odds favor the idea that Under Armour stock price will usually be between low and medium. So that's where it would be found, which means that it will generally not be expected or not be probably as high as IBM's stock price. Okay. Now, the example I'm trying to point out to you is that if I just put these two graphs up here and I said, hey, look at all these dots around low, medium, and high, and then low, medium, and high for Under Armour, right? You might say to yourself, what is this? This is just a bunch of dots. This is probability distribution, and I'm not sure I'm really getting. But the whole point of measures of location and measures of dispersion is by looking at all of these dots, you could say to yourself, oh, wait a minute. I don't have to look at the dots. All I need is this one number, the mean, the average. And I know that on average, IBM's stock price is medium, whereas Under Armour's stock price on average is low to medium, right? It's halfway between low and medium. So therefore, IBM tends to have a higher stock price than Under Armour's. So right then and there, you say to yourself, oh, okay. So I have this one number. On average, IBM stock price is 100. On average, IBM Under Armour stock price is 60. So therefore, most of the time, IBM has a higher stock price than Under Armour. That would be a measure of location. We'll get to that in a second. Okay. We're going to start calculating those in a second. But then let's say we also have this situation. I want to show you why measures of dispersion matter as well. Measure of dispersion, the word dispersion tells you how spread out data is, okay? Or how spread out something is. Well, if I can get all this to be erased, which there we are. Oh, almost. Let's look at two different probability distributions that have the same average. Let's say that this is IBM. And since most of the data is clustered here, this would be our average. Okay. We'll just call this medium again. Then let's call this Under Armour. Okay. So for Under Armour, most of the data is located all over the place, right? It still ends up having an average, right? The average is still about medium, right? If you took these and these, I mean, more or less, Under Armour's average would be still right here. IBM's average is more or less right here. But as you can see, right, Under Armour is way more spread out. It's way more spread out than IBM's. Okay. IBM's data, most of IBM's data is clustered right here in the middle, right? Most of the IBM stock prices or IBM's data is right around medium, whereas Under Armour's goes from low to high and everything in between, right? There's plenty of data points right here between medium and high. There's plenty of data points here between low and medium. There's plenty down at low. There's plenty at high. IBM, everything's right around medium. Under Armour, they're all over the place. Low, high, medium, okay? So in other words, if I asked you, hey, whose data is more spread out? You would say, oh, Under Armour. Under Armour stock price. It goes from low to high, everything in between. IBM's is like right around the average. So even though they both have the same average, medium, medium, one is much more spread out. If I asked you, okay, which one is more spread out? You would say Under Armour. And then if I asked you, okay, by how much? You would say, I'm not really sure. Right. Well, that's where we're going to come up with numerical calculations of just exactly how much further spread out it is. That's the whole point of having numerical measures, descriptive statistics for one, I sorry, for measures of location and measures of dispersion. Okay. So I'm going to wrap this portion up real quick before we come, then we'll start in with measures of location and measures of dispersion, right? This serves as our introduction to probability distributions and the importance and the need of measures of location and measures of dispersion. Okay, so to recap, what's a probability distribution? It's the combination of all the possible values that a variable can take on and the relative likelihood of that value occurring. Okay. So in other words, it's what's going to happen and how likely is it to happen. Okay. But then when you're presented with data sets, I'm talking big data sets like Microsoft Excel, where you have 40 columns and, 23,000 rows. You're going to want to be able to make sense of that very, very quickly. And in order to make sense of that very, very quickly, you really just need two things. You need measures of location and measures of dispersion. Okay. So to summarize the measures of location and the measures of dispersion, I have an analogy for you that will probably make pretty good sense. But again, measures of location, it's where is most of my data located? Where's the center of it? Where's the center of the data located? Well, the center of IBM is right here. And then the average of Under Armour, the average is also right there. It's in the middle. But how spread out is it? Okay. Well, for Under Armour, its data is way more spread out than IBM's. Okay. So therefore, we also need not just where is the center of it, but a measure of how spread out it is. Think about it like this. When you get on the highway and start driving, let's just pretend that your average speed is 70 miles an hour and somebody else that right? Maybe your best friend also drives on average 70 miles an hour. Okay, so most of the time, your speed is both around 70 miles per hour. Okay, so the center of your speeds are at 70. Okay, however, let's pretend that you love using cruise control and your friend absolutely hates it. Okay. So most of the time, you guys are both doing 70 miles an hour, right? So if I just came up to you and said, hey, what's your driving pattern? How fast do you drive? You said, oh, well, on average, I drive 70. My best friend, he or she also drives about 70. You go, oh, okay. Well, who's more erratic? In other words, who is more spread out? And you would say, well, you use cruise control, but your friend, is always speeding up, slowing down, speeding up, slowing down. So, in other words, even though both of you tend to average medium speeds, you're both doing 70 miles an hour, you are mostly clustered right around 70. You do 65 to 75. That's where your data is clustered. Whereas your friend goes from 70 miles an hour. So let's say you go down to 50, but up to 90, down to 55, up to 85, down to uh, down to 65, up to 75, down to 50, up to 90 again. My point is that that data distribution would be much more spread out than you, who gets on the highway, turns on cruise control, and just cruises down the highway at 70 miles an hour no matter what. Okay. That's the importance of having these descriptive statistics. Okay. Quantitative analysis requires us to have quick measures of location and quick measures of dispersion. And what that tells us very quickly, just by having, let's say, me and Tim, we both drive 70 miles an hour on average. But I love using the cruise control, so I'm always at 70, whereas Tim goes down to 50, up to 90, down to 50, up to 90. Okay. Why does that matter? Well, let's say you work in insurance. Let's say you are involved in the quantitative analysis of insurance. You work as an actuary for an insurance company. Well, if that's the case, you're not going to charge the person who uses cruise control the same insurance premium that you charge the person whose speeding is erratic. Why? People's whose velocity, I shouldn't say speed, but the velocity, people whose car velocities tend to be more erratic tend to get into more accidents, which means that you will end up charging them a higher rate. How did you get there? You got to the higher rate of their insurance because on average, they tend to get into more accidents because on average, their speed, their velocity tends to change more because they have higher measures, they have higher dispersion. Okay. Even though on average you both drive 70 miles an hour, the person who drives 70 all the time tends not to get into as many accidents as the person who changes their velocity quite frequently. And therefore, you can make better insurance decisions by just using two simple numbers. What's their average speed and what is the dispersion of their speed? And suddenly, the person who drives very erratically ends up being charged a higher insurance rate or insurance premium because they end up getting into more accidents and are a riskier driver. Okay. So, having said that, that's an introduction to probability distributions and why we need measures of location and measures of dispersion. In the next video, we're going to do measures of location.